Today we're going to do a little bit of a review on exponential functions. So remember back to when you graphed linear equations, they were in slope-intercept form, y equals mx plus b. You used the slope and the intercept to graph them, and what did that graph look like? It was always a straight line. That's the definition of linear, right? Straight line. So last year in 9th grade, when you worked with exponential equations or exponential functions, what happened with those? What did those graphs look like? Let's hurry and take a look. An exponential function, remember, was a slight curve. It either went up when you went to the right or it went down when you went to the right. You always had a starting value and you always had something that was happening to that value. So let's look at a quick example. Say that you started out with $10 and then you found a way to double your money each month. What would that look like on a graph? Well, if you look, we start with $10. I'm doubling my money each month, so after 1 month has passed, I would have $20. After 2 months has passed, I would have $40, and after 3 months, I would have $80. Now, none of the other points will fit on this graph that I have here, but this is going to continue to double every time a month passes. That's what an exponential function looks like, more or less. How about if you had a population of 100 tigers and each year half of their population vanished? What would that look like on a graph, and how many years before you had less than 10 tigers? Well, here's my exponential graph. I start with 100 tigers. The next year I would only have 50. The year after that I would only have 25. Then I would only have 12 and a half, right? It would keep going down by halves every time a year passes. So exponential equations had a specific format. You would have a total value, or I could say ending value. You would have a starting value or initial value. You would multiply that by what happens each time, so whether I'm doubling or whether I'm cutting something in half. Today we're going to take a look at percents right there. And then it was to an exponent of time period, so how many time periods have passed. So our tiger situation would look like y, which would be our ending value, equals 100 tigers that we started with, times our tigers are getting cut in half, their population's getting cut in half every time a time period passes, and x would be the number of years that have passed. So if I wanted to know, for instance, how many tigers there would be after 5 years, my equation would look exactly the same, but now the time periods that have passed would be 5. It's important to know how to write an equation, and knowing how to write that equation is sometimes every bit, if not more, as important as knowing how to solve that equation. So writing the equation is kind of what we're going to focus on. We're going to kind of focus on how to interpret that equation and how to get information out of it. Eventually, you're going to have situations where you can't figure problems out in your head, right? Or at least it would be an extremely long problem to do. It would take you days or years or whatever. And I don't think you're wanting to put that much time into it. So that's why learning how to write these equations are so very important. So here we have another example. Now we're going to start talking about percents. The population of a small town is increasing at a rate of 4% per year. If there are currently about 6,000 residents, about how many residents will there be in 5 years? So first of all, when you wrote an exponential equation, you had to think about what you already knew. We know that our initial or starting value was 6,000. What's happening each time period is we're growing by 4%, and how many time periods have passed would be 5. We want to be careful when we enter a percent. We'll talk about that in just a second. We want to know the total population after 5 years, So I enter the values that I know into my y equals a times b to the x power. Remember, y is my ending population. That's what I don't know. A would be my beginning population of 6,000. B would be growing by 4%. We'll talk about how to write that in a second. And X would be the 5 years that have passed. Let's hurry and look at this 4% increase. We all know that 4% as a decimal is 0.04. But if I only put 0.04 inside the parentheses, that only accounts for the 4% increase. It doesn't take into consideration all the people that already lived in the town. So when you're talking about growth and decay equations, you have to remember to include 100% of what was already there, then add or subtract your percent of growth or decay. So that's why I have 1.04 here. I had 100% of the people that were there. 4% increase. That's why the next year I would have 1.04% of the population living in the town. In order to solve an exponential equation, remember I have to do what's in the parentheses first. There's nothing to do there. Then I have to do exponent, so I take that to the 5th power. If I do that on a calculator, I'm going to get a big long decimal. I'm going to leave that number on my calculator screen and not round that number until after I multiply by 6,000. In the end, I would get 7,299.917, on and on and on. What's wrong with this number though? Remember, I'm talking about how many people are going to be living in the town in 5 years. Can I have 0.9 of a person? Well, not really, right? So I'm going to round to the nearest whole person and say that I have 7,300 people living in the town in 5 years. Let's look at one where we're reducing something by a percent. Let's say we want to reduce the size of a picture so that I can put it in a small frame. You aren't sure what size to choose on the photocopier, but you know that the photocopier can reduce the picture by 15% each time I scan it. If the picture was 10 inches long at the start, how long is it after 3 scans? This is an exponential equation. What do we already know? We know my initial size was 10 inches. What happens each time is decreasing by 15%. And how many times will we have done this? 3. We want to know the final size of the picture, or my total value. So if I put those values into my exponential equation, I get y for my ending value equals 10, which is my beginning value. We'll talk about the percent, and it's happened 3 times. I got 0.85 inside my parentheses because if I take 100% of my original length and subtract 15% each time, or reduce by 15% each time, my picture, every time I scan it, will only end up being 85% of the original size. If I just put 0.15 inside the parentheses, that means that my picture would only be 15% of its original size every time I scan it. And that's not really what it's asking for. If I want to solve it, remember I have to do the exponential part first. Leave that on your calculator screen and times it by 10. And I get about 6.14 inches after I've scanned it 3 times. Let's take a look. How about if there are ants in your yard and each day the number is increasing by 12%? You begin with 60 ants. What would the equation look like if you put it into the y equals a times b to the x power form? Try to write it down, see if you can get it right, and I'll show you the answer in just a second. Did you get 60 times 1.12 to the x power? Remember, A is your beginning value. B is your increase. Remember that you have to include 100% of the ants that were already there to the x power. Let's take a look at one more. If you have $2,000, that's what you start with, and your money is losing 4% each year, what would that equation look like? Remember, you have a decrease of 4%. Did your equation look like this? You have y, or I just wrote f of x since we're dealing with functions, equals 2,000 times 0.96 to the x power. Remember, on percents, if I'm increasing, I have to add my percent onto 100% of what was already there. So if I had a growth rate of 2%, in my equation I would put 1.02. If I'm decreasing or have a decay rate of 40%, I would have to subtract it from the 100% that was already there. So if I had a decay rate of 40%, in my equation I would put 0.6 for the 60% that's left. Remember to write this down in your notes. Write down any questions that you have, and I will see you in class. Have a great day.